Section 5.4, in the classroom I would teach this in a different order, but I'm going to follow the book order. So if we look at 5.4, it tells us that the enthalpy state function is the initial minus the final. And so what we do is we say delta H can now be equal to the enthalpies of the products minus the enthalpies of the reactants. So what do we want to start with? Well, we want to show you how we write equations. If I have an exothermic reaction, I will be having energy as a product, and you can see in the first equation, we write energy as a product. There is a second way we can write this where we separate out the enthalpy, and notice the negative sign because it is an exothermic reaction. We also can have endothermic reactions. That is where energy is one of the reactants, and as you can see, one way of writing this, we have it in the chemical equation, but there's a second way to write it where we have the delta H sitting by itself, and notice that it is positive because it is an endothermic reaction. So unlike the earlier sections, this is much more factual. We'll be showing a method. We're going to be applying the things from the beginning of the chapter. The other things I have to point out is that enthalpy is an extensive property. It depends on the amount. This was the equation in the slide before, but if I take this equation and I divide everything by 2, I'm going to have half the amount of enthalpy. And notice I also have a fraction, which we'll talk about in a moment. If I reverse the reaction, which I take this top equation and reverse it, what I will have is the enthalpy will be the same, but it will have a opposite sign. Since it was a exothermic reaction, now it is an endothermic reaction, it gets a positive sign. In the earlier sections, I talked about a phase dependence, and here's where I can show you. When I have a gas, I have one value. When I have a liquid, I have another value. And these are just things you need to know as you're going to solve problems. And all the mess we made about fractional coefficients in the early chapters. When you're working with thermodynamics, fractional coefficients are acceptable. You will see them in a later section as we deal with Hess's law. So 2 problems to wrap this section up. It says that aluminum reacts with iron oxide to make iron metal and aluminum oxide. So what you want to do is you want to list, what do you know? Well, we know we have 36 grams of aluminum, and it says 565 kilojoules of heat are evolved. If they are evolved, this is an exothermic reaction. What is it that you want? Well, you want to know what is the kilojoules per mole of reaction. So I'm going to show you a method that works. Some people like it, some people don't, but we ought to start somewhere. I will say minus 565 kilojoules, and I obtain them using 30 grams of aluminum. What I will do next is I will say that there are 26.98 grams of aluminum for every mole of aluminum. This is just a gram to mole calculation where we use molecular weight. Then what I'm going to do is use the stoichiometry of the equation. For every 2 moles of aluminum, where did I get that? Oh, from the stoichiometric coefficient. That is given to me for every mole of reaction. So again, this will be stoichiometry. And it's just something, it's a method that we use to do this problem. And what a negative 846.8 kilojoules, okay? Students have struggled with this in the past, and this will be used in the section on bomb calorimetry. It'll be a multiple step problem, but the last step will be finding the heat of reaction. So the things to note here are, what did we do to set it up? We put kilojoules divided by grams. What did we do next? Well, we used molecular weight to turn those grams per mole. And the third step we did is stoichiometry, where we were able to say how many moles of the material are in a mole of reaction. Again, you will use this in bomb calorimetry. What we come up with is the last slide, the last example I have is a different version of the same thing. It says how much heat is absorbed. You got that in the last problem. Here you want to find it, and you have a reaction of 20 grams of carbon with excess sulfur. So I'm just going to start setting it up. I'm going to say I have 20 grams of carbon. And hopefully at this point, you're beginning to learn to solve problems and you'll say, well, normally we turn grams to moles. So moles of carbon, 12.01 grams of carbon. That's using the molecular weight. Then what I'm going to do is I'm going to look at how many moles of carbon are there in a mole of reaction. I'm going to say 4 moles of carbon, and that's using the stoichiometric coefficient 4, for every mole of reaction. So again, this is the stoichiometry. And then finally, what I will do is I will use the delta H of reaction. There are, for every 1 mole of reaction, there are 358.8 kilojoules. Now, this is where people often leave off that word reaction. And as a beginning student, it's going to frustrate you because you're going to want to have everything laid out, but you'll just have to, once again, trust me. It comes out to 149 kilojoules. So one of 2 types of problems can occur on your midterm. It could be the one from the slide before, or it could be this one. What I did was I started with the number of grams. Using the molecular weight, I turned it into moles. Using stoichiometry, I made it into the moles of reaction. And then finally, I used the delta H of reaction in order to come up with the number of kilojoules. Now, this is where it's factual, it's methodical, it's problem solving, but it gives you insight. In a Gen Chem class, we don't compare a lot of things. But as we progress further in the course, in Chapter 7, in intermolecular forces, comparisons are made. So if you get your problem-solving skills down here, it will be a lot easier later. As usual, please ask questions.